So let us start the discussion today. So if you look at the space system, it has a multiple dimensions. The top side, you can say there are technologies, and bottom side, there are applications, and they all cater to the core, which is social and economic benefit. So all these things are done to derive certain set of social and economic benefits. And today's topic covers the technology elements as well as application sector of the space system. So let us start with a question that we all wonder, what is satellite? So moon is one of the satellite which revolves around the earth. So in that sense, any natural or man-made object moving around any planet in a predefined path in space can be considered satellite. And what we are going to talk today is about the artificial satellites, which are man-made. So we always wonder what makes the satellites to revolve around the planet. And there are different kind of paths around the planet it can take. Like we have the satellites which are very close to the earth. We have the satellite maybe around 500 to 1500 kilometers away from the surface. We have the satellites which are few thousand kilometers away, and we have a satellite which is called geostationary, which moves with earth. So that is around 36,000 kilometers away. So the basic principle remains the centripetal force equal to centrifugal force. If that can happen, then we get the stable orbit. And when I came to know that this talk is for the teachers, so I pulled out two slides which I always give to the students. So a little bit of orbit creation, how the orbits are created around the earth. So this is a very simple form you can understand from the 10th grade maths. So you can recall the equation of motion, which is nothing but S is equal to ut plus half gt square. And if we try to solve it in a very simplified manner and pose a question, how much ball will fall in 1 second under the ideal condition if there is no air, nothing else deviating its path? So the number comes around g by 2. That means approximately 5 meters. Now let us say I try to throw the ball in the horizontal direction, sitting on the peak of the Everest. So can I avoid the ball hitting the ground? So the answer is yes. You can throw the ball, gravity can still pull it, but you can avoid the ball if you can throw it fast enough. Now I will show you a simple calculation. What is fast enough? So if you look at the right side diagram, it talks about the curvature of Earth. So if you look at the curvature of Earth, it falls by about 5 meters below horizon every 8 kilometers. So with this, one can infer that if the ball can be thrown in such a velocity in horizontal direction that it travels 8 kilometers in 1 second, then it will fall by 5 meters in the downward direction. That means every second the ball is traveling 8 kilometers and falling by 5 meters. Earth curvature is also going by 5 meters, so it will never touch the Earth's surface. So in the real sense, orbits are nothing but a way the object is falling towards the Earth, but it is never touching the surface because the velocity given in the tangential direction is just right for that distance. So this is the paradox or fact you can debate and discuss with your students later. Now let us move to the main topic. Today I am going to cover the communication as well as navigation. So we'll start with the question that why satellite communication? Now we have many means of communication, cell phone, the internet, and so many other means of communication. But satellite communication also is required because the human activity is increasing across land, sea, air, and space. And traditional means of communication, they do not necessarily cover all these things, especially if you go for the difficult region of land, deep in the sea, up in the air, and deep in the space. These are the things which are the very, very special use case of satellite communication. And it has a very unique advantage. One satellite can cover a very wide region. It can give the remote area access. It can be connected to a moving platform without any problem. And it has a broadcasting capability. DTH is one of the example, direct to home. All your drawing rooms are now equipped with the satellite broadcast receiver. And it is very, very reliable because the satellite is not impacted by the natural disaster. So the satellite is up in space. Of course, it has some other uh, reasons to worry about, but not the reasons which are generally damaging the communication system on the surface of the earth. Now, it is important to know how we started in India. So the satellite communication history goes as deep as 1960, when Dr. Vikram Sarabhai started thinking about it, and he collaborated with NASA. We did certain experiment where the Earth station was set up right here in this campus in Ahmedabad in 1967. And there was a very big satellite instructional television experiment called SITE, was conducted in 75-76 time frame, and this was the first example of DTH. You can see the dish there in the, let me put the uh, pointer in the laser mode. So this is the dish which you can see is the dish which works at the UHF frequency, and it's used to receive the TV signal right from the satellite. So this was the DTH of 70s. ISRO did it way back. Now, this is the story which covers our early days from the 1980s to till date. We started from a small satellite called Apple, and which was experimental satellite, followed by a INSAT-1 series of satellite which were procured from US. Then we started building INSAT-2 series of satellites. That's where I got involved in the all this game. And then we kept on enhancing the satellite capacity in terms of frequency, in terms of power, in terms of coverage, in terms of capacity. And today we are sitting in 2024, where we have the most modern satellites designed by us, and they are going to be launched very soon, uh, and which can provide internet to your home. So it is much beyond what we are having today, which is television to your homes. Now, the communication satellite generally utilizes three types of orbits. One is called geostationary, which is most popular orbit, and you need three satellites to cover whole globe. That is the leftmost picture depicts it. It is having the orbital angular velocity exactly matching to the Earth angular velocity, so that it is always stationary over any point, so you don't need to point your antenna here and there. The second option is medium Earth orbit, which is 8,000 to 22,000 kilometers. As we come closer towards the Earth, our coverage shrinks, and we need more number of satellites to cover whole Earth. And the LEO satellite, which is about typically 5 to 700 kilometer orbits. Now Starlink by Elon Musk is one of the example of the LEO satellite constellation, which is used for communication. OneWeb from the Bharti Airtel is also Indian satellite constellation, which is going to be used for the satellite communication. Now, looking at the satellite communication system picture view, uh, you have a satellite in space, you have a systems on ground, earth stations and the user equipment, and you have a channel in between from the earth it will pass through the atmosphere, ionosphere, and then to the free space. And the whole system is designed so that you get the desired communication quality to your earth station, taking care of large distances and the impairments caused by the atmosphere and ionosphere. Now the right side you can see these are the some of the first in the global scenario. 1962 the first communication satellite, and the India's communication satellite is Apple first. So this is the picture of snapshot of what we have today. We have more than 18 satellites in orbit, positioned at different geoslots. They are allotted by International Telecom Union to us to provide the services over India and around. Now, when we talk about the services and applications, so there are, depending on the how we are going to transmit and receive the radio wave and how our ground stations are designed, there are different class of services which can be provided by the satellite. The most popular is fixed satellite services, mobile satellite services, and broadcast satellite services. These are the three categories which are very popular. But beyond this, we have the earth exploration satellite services where we do the data downlink from the satellite to ground. Then space research services, space operations services, radio determination services, inter-satellite services, communicating between satellite, and so on. Now, this slide shows how the satellite and ground systems are interconnected to provide a particular service. So if you look at the fixed satellite services, let us say we want to exchange the information from the, let us say, the aggregation of telephone calls from one city to other city. Then all the calls will be aggregated at telephone exchange. It will go to a satellite gateway, which will uplink it to satellite. Then satellite will downlink it to the station, let us say located in another city, and the reverse process will take place. Then the mobile satellite services, where we have a very small handheld or a portable type of user terminal. This also works on the similar connectivity principle. The user will send the information to the gateway. Gateway will recover the information and send it back to the other user. Then any information originating from the mobile user 2 will also follow the same path to the user 1. Third is the broadcast satellite services. Now this is the most revenue generating services because the one satellite can cover the whole India, and there is no limit on number of users because all the information which is broadcasted is available to everybody. Where in the previous two services you have to have a dedicated radio frequency spectrum available for each user. So as number of users shoots up or the information amount shoots up, then there will be a limitation on catering the number of users. Now, how the satellite communication systems are designed? The basic principle is it starts from the application. A different kind of users, they dictate different kind of application. Commercial users have a different application. Government or defense type of users, they have a different kind of application. So as a system engineer, we map it to the certain technical requirements and then work out the certain architecture, which finally leads to various class of satellites. The latest class of satellite is high throughput satellite, where the large bandwidth is available, where we can use them for the internet service provision and video broadcasting, video conferencing, and so many other applications. Now, this slide just captures the major technical requirement. Let us say if you are trying to talk about a satellite communication system, what all you should worry about? You should worry about what type of signals you are going to service. Is it voice, data, telemetry? How many users you want to capture? That will tell the capacity of the system. What area you want to cover. Then what type of ground segment, whether I can have a very big ground segment, or it should be handheld, or it should be like installable in my home like DTH. What quality of service you are targeting, uh, what kind of connectivity you are looking for, the way I have shown in the previous diagram. Then the most important thing is the availability of the system. What is the downtime which is acceptable to you? Then latency. So sometimes the latency becomes very important when you are talking about very high data rate communication, or when you talk about the voice communication. So in such cases, the low Earth orbit satellites which are near to Earth, which are offering some few tens of milliseconds of latency, they are preferred. Then of course operational life, then certain special requirements like whether you want encryption or jamming, security, and so on. Then coming to the satellite part. So if you look at this diagram, the spacecraft is divided into two parts. One is called payload system, another is called bus system. So the payload system is the set of the equipments which are used for the communication or navigation, and the bus system is like all the accessories, all the parts of satellite which are required to support the payload functions and its maintenance for 15-year, 10-year in orbit, protecting it from the harsh environment of space. Now this is how the satellite looks like in the orbit. This is the example of our first direct to home service satellite, INSAT 4A, built in India by ISRO, and this is how it looks like in the space. But if you expand it, it is of the various parts are there, and the payloads are always housed on panels. They are called north and south panel, like here and here inside and on this panel. Now the communication payload or transponder, popularly known as transponder, you must have heard all these terms. So its function is it will receive the signal from the earth, process it and retransmit it, and it basically consists of antenna which connect the electronics to the free space, and we are able to connect to the ground station on earth. Now if you look at the hardware which goes inside, there are different kind of antennas which are used. Then antenna delivers the signals to certain set of hardwares like receivers, low noise amplifiers, filters, and finally we power amplify it and again combine all the signal and send it back to earth through antenna again. Now these are some of the pictures of in our lab, like one satellite panel which is populated with the several equipments, and they are very specialized electronics hardware, mainly radio frequency hardware, and several such panels are built and then integrated in this fashion. And finally these panels are added with other satellite parts, and this is how a full-fledged satellite looks like on Earth. In space, the solar panels here and here will get deployed, and you will get the solar power from them, and these are the antennas, and they are covered with the special material so that it doesn't get heats up and cool down beyond the acceptable limits. Now coming to the SATCOM applications. So there are many applications of the satellite communication, the video distribution, the DTH, then the video contribution, where you can see that today all the news channels, they have the direct satellite news gathering terminal which are positioned in any event, and they directly connects the studio to the news gathering fellow, or it can directly go to the satellite for the broadcasting. Then we have the consumer broadband as a very upcoming application, and enterprise network. The many enterprises, apart from their terrestrial network, they also deploy the very small aperture satellite terminals, especially in the remote areas for the connectivity, seamless connectivity across their enterprise. Then cellular backhaul and trunking. Today the cell phones are mushrooming, but the intercity connectivity, the satellite communication is one of the very popular means of backhauling, especially when there is one village in the remote and there is not it is not able to get connectivity through fiber because of the geography. The one small satellite terminal can do the trick. Then the military satellite communication. In the Ukraine war, it was proven that when all other satellite communication means broke in the war in the Ukraine, the Starlink satellites, they were used for the connectivity. Then the land mobility to the, like in the moving trains, in the moving vehicle, you can have the communication, you can have the communication in the aeroplane. You can have browse internet in aeroplane via satellite, and same thing is true for the maritime connectivity. The one is the mobile satellite network for the vessel communication. So the ISRO has created the whole system, satellite, the hub station, as well as end user terminal. They are deployed on the various ships and they can have their position reported. They can be tracked sitting on the ground. They can even get the weather information on those terminals. They can even press SOS button and then they can get the rescue support and so on. So there are so many applications for the mobile satellite communication, and this is done in the lower frequency band of around 2.5 gigahertz, that is S band. Now aeromobile also has the similar application. So SATCOM has no alternative and no substitute for the aeromobile and maritime. So the aeroplanes nowadays are getting equipped with the communication, navigation and surveillance infrastructure, especially after the Malaysian aeroplane which crashed, and today also we don't have any clue what way it went, what way it flew. So the aeromobile communication is also one of the very popular application. Now we are talking about 5G, 6G networks coming up. Now these upcoming 5G and 6G networks, there the satellite will be integrated seamlessly. So as an end user, you will never know whether you are using your call or your internet is getting fed with satellite or the terrestrial network. So there are four major applications. One is trunking, backhauling, then communication on move, and then video and data communication merger. Now we have another very important application called automatic weather station. More than 400 weather stations are, not even 400, maybe close to 1000 stations are deployed all over India, and they collect humidity, wind velocity, temperature, and sometimes soil moisture and all other parameters locally, transmit it to satellite. Satellite send it to Indian Meteorological Department hub station, and this is also used in the weather forecast modeling. So this is one of the very important application, and we have a dedicated satellite transponder for this. Now satellite based search and rescue. There is an international system called COSPAS SARSAT system where we have the multiple satellites. Anybody who is in the distress, either on the land, sea or ocean, they can press the button of their beacon, which is here on the left side, and beacon will transmit the SOS signal, save our soul signal, along with its position, coordinate and identification, etc. And the system will forward this message to the nearest rescue station, and the person can be rescued. And every day there are few incidences are happening and people are getting rescued. The India has also its own contribution to the search and rescue system. So we have in our geo satellite the transponder, and we have the ground system which is called distress alert transmitter, which you can see here, which can be given to the ship or to the fishermen, and the fishermen can get the message, and they can, in the local language, any warning which is being issued by the because of the bad weather and all. So this is also one of the very important use case, has very high social impact. Uh, Coming to another application of the satellite communication is ADS-B. Now when the aircraft flies, the air traffic controllers, they get the aircraft position, velocity, and many other information ID in the line of sight mode. But there is no, it is covered only on the 70% of the positions of the whole aircraft movement corridor. 30% are still uncovered. So the same signal in this system is picked by the satellite in space and decoded and send it to the ATC. So the coverage can be improved to 100% by using the satellite based ADS-B system. We have already demonstrated in one of the small satellites recently launched by a small satellite launch vehicle D2 flight, and it has detected several thousands of aircraft when we were experimenting that payload. Now there is one more satellite-based application called satellite-based automatic identification system. Now all the ships which are more than 300 ton, that size, they are mandated by International Maritime Organization that they should transmit their information to all the neighboring ships, and then neighboring ships, it transmits the information so that all the ships in the vicinity of few nautical mile, they know who all are there around them, and in case of any emergency they can be contacted. But uh, in the when this cell is, let us say there is a ship which is of enemy ship, they will switch off their AIS transponder, and it will not be detected by the neighboring ship. So to take care of this, there is a system called satellite based AIS, which will detect all the ships which are close to our borders, I mean the close to our Indian land borders towards the ocean, as well as detect the ship which is not uh, detect let us say we are using the imaging satellite and AIS satellite, and inferring that I am seeing one ship in the image, but I am not getting the AIS information. So that ship is the ship probably from the unfriendly nation or unfriendly ship. So the required mitigation measures can be taken. So the AIS from the satellite gives a holistic picture around the Indian land borders in the ocean. Now, there is one more application, the communication intelligence. Let us say you want to understand what are the communication going on uh, over your land, or let us say in the adjacent geography. We can pick the signal from the space and decode it and forward it to the proper user who can utilize it to in case of intelligence and surveillance. So this is a defense application where we are trying to capture the different communication system signals emitting from various geographies. Now this completes the presentation on the satellite communication system. We will move to the navigation satellites and its application. So navigation is not a very simple concept, so I would like to give a little bit of technical background. Uh, Basically, the navigation system works on the triangulation or trilateration concept. Uh, what happens? Uh, you have the satellites emitting the signal, and we have a ground receiver that also generates the similar signal and tries to measure the time delay of the signal coming from the satellite to here and measures its range. And from the range I will explain later how it calculates its position. If you look at the picture on the top, uh, there are three towers emitting the signal and there is one receiver. So if it can measure the distance of the tower, known location tower, from 3 points, it can compute its position in 2 dimensions. Now, just to make it simple, let us say I make a statement that I am at the location which is 337 kilometers from Bangalore. So I can be anywhere on this circle, right? Now I make another statement. I am 469 kilometers from Thiruvananthapuram. So I can be any other place on this circle, but the intersection of these two are the valid solutions. So I am either here or here. So to know the exact location, I have to make another statement that it is 169 kilometers from Velankeni. So this is the location which is the intersection of these three circles. So now somehow if I am able to make my measurement, position measurement with respect to this point and this point, I will be able to calculate my location here. So same thing is done in 3 dimensions by satellite. Let us say you have two satellites and the user is, let us say, 36,000 kilometers away from the satellite. So the user can be anywhere on this sphere for this satellite. Same thing is true for this satellite. So so there can be an intersection of these two spheres which will be a circle. So the position can be anywhere on this circle, which is a 2-dimensional big circle which is perpendicular to this plane. Now if I add third satellite, so these three spheres now will intersect that circle. The third sphere will intersect the circle at these 2 points. And the one point will be on the surface of Earth and other point may be inside the surface of Earth. And the receivers have the intelligence to know which of these two solution is a legal solution. So the whole satellite navigation system works on the principle of measuring the distance from the three known satellite locations. So the distance, you don't have any tape to measure. You don't have any laser ranging to do that from the cheap receiver from your cell phone. So what you do, you actually measure the time, and from the time we infer the distance. So what happens, the satellite sends a code at a given time and the receiver simply measures how much time has elapsed in the travel, and from there it calculates the distance. Now that means everything is depending on the time, so the time measurement should be very, very accurate. So just to give you the idea of the accuracy, so if your time measurement is off by 10 nanosecond, your position will be off by 3 meter, because the velocity of light is so fast. So in order to do that, you need a very, very precise clock which maintains the time, which is called atomic clock. And there are various types of atomic clock which is being used. But the clock is not used at the user receiver because the user receiver cannot be so bulky, it cannot be so costly. So what, okay, let us say this slide shows the actually in the system what happens. We need minimum 4 satellites to calculate its position and time. So to calculate the range from this point to this satellite, you will apply this simple equation that xi minus x square, yi minus y square, zi minus z square is equal to c into the delta t whole square. So with this, you will be able to measure the distance of this receiver from the 4 satellite. So if you have 4 equations, you will get 4 solution x, y, z and time. So if you only wanted to know the position, 3 satellite is good enough. But if you want to calculate the velocity also, time dependent position, so you will need 4 solution t. So that is why minimum 4 satellite is required to do a meaningful navigation. Now in the navigation system architecture, there are 4 segments. Like in the communication, there were 3 segments. Here we have 4 segments. So one is the space segment, of course, the set of satellite. Then we have the master station, which controls the whole network, and monitoring station, which monitors. So in the satellite navigation system, we are using lower frequency. So there are various impairments which affects the accuracy. So we have to do lot of monitoring, mathematical modeling of everything, and transfer everything to the master control station, and the control station will uplink all these parameters, and those parameters will be embedded in the signal which we have seen previously to the user receiver, and user receiver will use all those information to apply appropriate correction in the computed information. Now if you look at the global scenario, there are 3 types of navigation system. One is GNSS, Global Navigation Satellite System, Regional Navigation Satellite System RNSS, Satellite Based Augmentation System. So in the first category, this is called Primary Navigation System, where the satellites are directly used for the positioning, and it gives the global coverage. Anywhere in the earth, service is available. So GPS from US, GLONASS for Russia, Galileo from European, Compass from Chinese is the example of GNSS system. So now coming to the, hello, am I audible?
Yes sir, it's fine.
Okay, so coming to the regional navigation system, our own NAVIC, which is Indian Regional Navigation System, then QSIS, which is Japanese, then BeiDou, which is Chinese. So they are designed to cover a specific region of interest. They can manage with the smaller number of satellites like 6 to 10, whereas previous systems, they need minimum 24 satellites to provide the service. Then satellite based augmentation system. Now if you want to use the navigation signal for the safety of life application like aircraft navigation, its landing, en route navigation, and many other application, you cannot directly use these GPS or IRNSS signals. So what you need an additional system which is overlaid, which adds certain more information given to the user receiver, so that your confidence on the using those positions, those navigation signals which were coming from the primary system, improves. And you also have the monitoring of all the satellite by this system. If there is any bad satellite, it will flag, it will give the early warning that these signals should not be used, switch to manual mode, and so on. So India has its own system called Gagan. VAS is the European system, EGNOS is the European system, MAS is the system from the Japanese. And there are few more systems coming up across the globe. Now this is our journey to the navigation system. We started with the Gagan actually and got it's operationalized in 2015. And in the meanwhile, we started our regional navigation IRNSS system design. And first time we achieved the first position fix. That means minimum 4 satellites were in orbit in 2015, and in 2016 we have completed the constellation. The navigation, our IRNSS system is now getting upgraded with the new signals and more powerful satellites and so on. We also use the provide the services on the similar frequency band where the global systems are providing, so it is interoperable. Any receiver can use, which is capable of receiving GPS, can use IRNSS signal also. Now this is the picture of constellation of the 7 satellite, and these are the different kind of receivers which were developed, and these are the different kind of application equipment which can be used for the vehicle tracking and so on. This is the picture of the satellite in the clean lab before it moves for the launching. And we have a navigation center which is the master control center at the Bailalu, Bangalore, which takes care of managing the whole IRNSS network. Now this is the constellation view at the different geolocation. We have the 3 satellites which are exactly in the geostationary orbit, and the 4 satellites which are in the inclined orbit, and this gives me the enough number of satellites visible over Indian mainland, and also very good geometry. One of the very important fact for getting the satellite navigation, improving the satellite navigation accuracy, that the signal which you are receiving from the various satellites, the satellites should be far apart with respect to your location. So the system is optimally designed to give a very good look geometry from Indian region. Now this is the Gagan, which is called GPS added geo augmented navigation. We have this system placed in the 3 of our geostationary satellite called GSAT-8, GSAT-10 and GSAT-15, and we got the certification where this system is certified for the en route navigation of satellite. There are different certification number called RNP, required navigation performance 0.1, and the precision approach with vertical gravity, which talks about certain standards which is used by the Airport Authority of India based on the international standard, and we are the one which will fill the gap which is existing between currently IGNOS and MAS. So any aircraft which enters in our region can use the Gagan system. Now the Gagan system view looks like this: 3 geosatellite, 1 uplink station. The uplink station is fed by the various data collected by reference station and all those correction, the position of atmosphere, various errors. Those things are uplinked to the geosatellite, which downlinks it to the aircraft or anybody on the move, which is having the SBOS receiver, and they can use this system for their safety of life application. Now coming to the technology part, the IRNSS payload is equipped of L5 and S band transmitter. It is only transmitter, it doesn't receive the signal, and the L1 signal is added in a new NAVIC series to make it fully compatible with the GPS type of system. And second is we need to range the satellite position accurately, so we have the ranging transponder. Then the Gagan system is equipped with, again similar, we uplink in all the information which has to be downlinked in the same L1 band and L5 band. These are the signals which are at the frequency around 1.2 to 1.5 gigahertz. Now this is the simple view of the navigation payload. So there is a on board, we generate the signal and transmit it through a high powered transmitter over the India and about 1500 kilometer beyond our border. So for the S band and L band we have used two frequencies, and onboard system, the heart of the whole system is atomic clock, and we in India have successfully developed our own atomic clock right here in the Space Application Center and flown it on the NVS-01 satellite, which is working fine. Now coming to the satellite navigation services. Now there are three types of services. One is basic services, which is position, velocity and time. The second is auxiliary service, which is like uh, added value added kind of services where authentication, like in the PVT service in the previous, it is open access, it can be used on your cell phone. uh, PVT services are also available. We have two types of signal in our navigation. Actually whole thing started in the Kargil war, when the Indian defense could not use GPS because they denied the signal for us, and government of India decided to bring our own navigation system. That is where the ISRO was given responsibility to bring the IIRS system. So we have two types of signal, one which can be accessed by any user from any country of any category. Other is restricted services, which can be only used by the one who is authorized. It is an encrypted service. Everybody cannot use. It has a very different signal structure, very different in encryption and coding scheme. Now, there is a concept called service provisioning volume. So we get the terrestrial service means around us, and the space service like up to moon also people are using the navigation signal. Now in the auxiliary service, the high accuracy services are required where you may need the centimeter kind of accuracy. Generally the position accuracy of primary positioning system is 3 to 10 meter at the best. But if you want the centimeter kind of application, or if you want to go to millimeter kind of application, you have to do something more to the system, add certain element terrestrially and provide those services. Then there are the application specific services, which is like I called Gagan, the SBAS. Then the satellite aided search and rescue services, the emergency warning services, like you can do the geofencing. So the moment, let us say, Pakistan used to capture a lot of our fishermen, but the moment we have put a system where its coordinate is calculated and the moment it crosses our border, the emergency alarm will go to the fishermen as well as to the station at the coast that somebody has crossed the safe water. So these are the things which can save life. Now this slide we can skip. This is just the summary of what I talked uh, today. Now look at the SatNav market. It is a multi-billion market in the ground segment, and the whole globe there are so many services which cannot run, like even you cannot order your food today, your Amazon delivery cannot happen. There are many things. So the knowingly or unknowingly, satellite navigation services has entered in our life. We cannot drive without Google Maps, and so many things. So this has the multi-billion dollar market, and India is also trying to capture its own pie in this. Now if you look at the strategic application, the defense aircrafts can use this. It can be used to guide the weapons, and it can be used to maintain the timing of the defense communication network and so many things. In the civilian domain, as I talked, even in the agriculture, it has the application where they do the seeding, they do the spray of the paste in the field. in the aviation, in the space, in the train, moving train, ships, the insurance and finance, communication network, they use the navigation signal. Even power grids, they use the navigation signal for the synchronizing the grid frequencies across the national grid. You will be surprised to know that the SatNav application, they touch, so there are sustainable development goals set by UN, 17 goals, and most of the goals are scattered by navigation also. So satellite navigation is also one of the means to attain those sustainable development goals. Now timing, I was just telling that the telecom networks, they do the synchronization based on the GPS signal. The power grids, they do the synchronization based on these networks. Then there are scientific applications of timing where you are trying to do some astronomical event time tagging across the globe. You are observing from 2 points wide separated on the globe, and you want to know whether they happened at the same time or at the different time. So you need a very precise time synchronization among them. Then the satellite based remote sensing also is having the navigation signals. They can be used as a reflectometry radio occultation type of application, and such like the navigation signals, when they are passing through the atmosphere and they are captured on another satellite, you can infer certain things about the atmosphere. And uh, even for the earth deformation, if you can deploy certain millimeter accuracy receivers and monitor the earth deformation, how it is going to happen. Then there is a combo application where the satellite communication and satellite navigation both are merged together. So the position is transmitted in the real time via satellite, because you are not getting the terrestrial network all the places, especially in the scenario of distress, in the scenario of, let us say, railways. So railway has deployed the real time track tracking information, which uses the navigation satellite along with our MSS GSAT-6 satellite, and with this they are tracking more than few thousand train as of now. And same system has been experimented for real-time aircraft tracking. And satellite based personal trackers are also evolving, and this is upcoming IoT application where a small form factor device, low power device, can be part of a let us say a soldier or a rescue worker working in a remote area, or let us say somebody working on a oil rig, and they can be tracked. And this can be used for the asset tracking also of various companies who are moving their transport fleet all across India, their ships all across globe. Uh, the maritime domain awareness is one of the very important topic, especially in the defense domain. Uh, that also can be used as a combination of satellite communication, satellite navigation, and Earth observation together. So you use the imaging signal, you use the positioning signal, you use the communication signal, and create a common comprehensive view of waters all around us, so that you are able to detect and neutralize the threat in the at the earliest. So this completes my presentation. So thank you for your kind listening.